everybody. So today I'm going to talk to you about acids and bases. This chapter is really involved. It actually encompasses 2 chapters in the textbook, but the textbook being the AP textbook, it incorporates chapters 16 and 17. But today what I'm going to really talk to you is just some of the basic background information, some of the important things that you should know to sort of lay the groundwork for the rest of the unit. So something that's important about acids and bases, and I think that we forget this because we do a lot of the math and we kind of study them on paper, are some of their properties. And so listed here on this first slide are a bunch of properties. Acids, they taste sour. That's really for weak acids. If you've ever had a Sour Patch Kid, if you've ever had grapefruit or any citrus fruit, they have that sour taste to them. They react with metals, the acids. They form hydrogen gas. And the equation for that one, if I were to write that in here, would look something like this. We would have like a metal like magnesium plus an acid like HCl, and this would form magnesium chloride and hydrogen gas. There are certain acids, like nitric acid, for example, that will react with metals, and they actually form different gases, particularly nitrogen dioxide, which is this brown poisonous gas that's produced when you put a metal in nitric acid. You could also have a mixture of acids, something called aqua regia, and aqua regia is where you have hydrochloric and nitric, and that mixture of acids is actually able to dissolve really precious metals like gold. But most metals, if we put them into an acid that is not nitric acid, so HCl, if the acid is, or if the metal is reactive, it will react with the acid and it will dissolve. Gold is pretty inert, and so gold, platinum, silver, copper, those will not react with acids under normal circumstances. You would have to use nitric acid. Some other properties here, the acids turn indicators colors. We'll talk more about indicators later on, but some of them you already know. The big one that you know that's used all the time is phenolphthalein. Acids can also neutralize bases, and so the reaction for neutralization, which again we'll spend a lot of time doing, would be something like acid, like HCl, plus base NaOH, yields water H2O, plus a salt NaCl. Acids are caustic. That means that they could really damage tissue. If you were to get acid on you, it will cause chemical burns, especially if it's one of the strong acids. And it's not fun. If you ever get acid on your skin, you would want to rinse it off really, really well with water. But importantly, you'd want to neutralize it quickly with a weak base. Bases, some of their properties taste bitter. So soap actually is a basic compound. If you've ever tasted soap or gotten some in your mouth on accident washing your face, then you might have tasted the bitter taste to it. Another substance that contains bases or basic compounds are those leafy greens like endive. And endive, when you eat endives, it has a bitter taste to it. Bases are slippery, so soaps have that slippery texture to them. Bases can neutralize acid. They also turn indicators colors as well, and they are caustic. Some common bases, sodium hydroxide, ammonia, and then one that you may not think about, bleach. Bleach is also a basic compound as well. So what happens when acids and bases dissolve in water? Well, they dissociate and they react with the water. And this first equation that I'm showing you here, HA plus H2O, well, that shows how the acid reacts with the water and it forms that hydronium. That hydronium ion is what really causes the acid to have all of these properties that we talk about. The caustic nature of the acid is due to that hydronium. The low pH is due to that hydronium. Now, there are different definitions for acids and bases. When we reviewed in class, a lot of you were mentioning these. And so here they are again. The first and simplest definition, the Arrhenius definition. This shows an acid as having an H in its formula, and it associates to form either H plus or H3O plus. If it is a base, it has an OH minus hydroxide in its formula, and it will form OH minus. Be careful with this one because the AP exam, the IB exam, they love to throw in alcohols where they, and ask you if it's a base. So you'd have something like CH3OH, and this compound has a hydroxyl. It doesn't have a hydroxide, and so that hydroxyl is not going to form OH minus. That CH3OH, that methanol, that is not a base. The other definition, which is the one that we generally stick with, and this is the one that we see all the time and the one that you really need to know, is the Bronsted-Lowry. And the Bronsted-Lowry treats acids and bases more like a reactive agent and defines the acid and base based on its reactivity. So HCl, that will react with water, and it will react with water by donating an H+, and that's how they would define an acid as an H+ donor. And the base would react with the acid, and that would accept H+. So we see here that the HCl, if we highlight this, the HCl, when it reacts, it changes into Cl-. Well, how did it go from HCl to Cl-? It must have actually given up an H. And so we can see that the HCl donates its H+ to water, and that makes this HCl an acid over here. The water, on the other hand, it acts as a base, according to Bronsted-Lowry, because it will accept. And so the water accepts an H+, so it acts as a base. Now, if we go in reverse, we see that the Cl-, that this accepts an H to become HCl, so this acts as a base. And the H3O+, this acts as an acid. The idea is that you will always have an acid and a base on each side. You'll always have an H+ donor and an H+ acceptor. And that reactivity is dynamic. You have that going in the forward direction and the reverse direction. So this shows you the HCl and the H2O reaction. We see that an proton donor is going to be an acid. A proton acceptor is going to be a base. Here I list some proton acceptors. These all have the ability to accept an H+. They generally can do this because they have a lone pair, and that lone pair can form a coordinate covalent bond with the H+. So here's a specific example, and this one's kind of neat because it doesn't actually have any water in it. It's showing you an acid and a base reacting, probably in aqueous conditions. But this H2S, if we highlight it in orange, it becomes HS-. That means that the H2S lost a hydrogen and acts as an acid. If we go in reverse, the HS-, it accepts an H and it acts as a base. If I highlight the other two species, the ammonia and the ammonium, in green, we see that the NH3, that one actually accepts an H and becomes NH4, so it acts as a base. NH4 donates NH and goes back to NH3, it acts as an acid. These are called conjugate pairs. So we have the pair in orange, and we have the pair in green. Every acid is going to have its base pair, its conjugate base, and every base is going to have its acid pair, its conjugate acid. You'll see that they're always on the opposite sides of the equation. So you can't have an acid and a base conjugate pair where you have H2S and an H3. They're reacting with each other, but they're not pairs of each other. Another way to quickly, eyeball these is to say that the conjugate base, it's going to have one fewer hydrogen, and it's going to be negatively charged compared to the original acid. Everything else is the same. The only difference is the one difference in H and the one difference in charge. Now, I'm going to stop here for this video. The next thing we're going to talk about is acid strength, and we'll do that next time. But what we can practice in class is really writing out these equations and identifying the acid-base pairs and talking about the properties of acids. All right, thanks so much for watching.